began an important theorem in this real analysis. In the analysis whole of this branch, another important result is monotone convergence theorem. Monotone convergence theorem. For this, we first define what do we mean by a monotone sequence. Let me first define. Suppose we have a sequence xn be a sequence of real numbers, then we say that this sequence xn is increasing if we have the following order for the terms of the sequence: x1 being the smallest, then x2, so on, greater than the x1, x3 greater than x2, so on. We have this order of the terms of the sequence. If this is the situation, then we say that such a sequence is an increasing sequence. And we say that this sequence, we say that this sequence xn is decreasing if we have the reverse order in reverse order for the terms of the sequence according to their indices. X1 needs to be greater than or equal to x2, greater than or equal to x3, greater than or equal to some nth term, and this nth term greater than its next term, and so on. We have this thing, and this will be known as a decreasing sequence. And if a sequence which is either increasing or decreasing will be known as a monotone sequence. So what is a monotone sequence for us? Let me name it. Monotone sequence is either increasing or it is decreasing. Increasing or decreasing sequence. Decreasing sequence. So these sequences are very important in analysis, as we will see in the monotone convergence theorem and its subsequent applications. But let me first give you some examples. As can be seen that this sequence 1, 2, 3, 4, so on, it is clear that the sequence terms of the sequences are increasing with the indices, hence it is an increasing sequence. And for the increasing sequence, I'm going to bring this notation using upper arrow heading towards upside, and for decreasing sequence I will use the arrow towards downside. So with this notation, this is an increasing sequence, and let it give one more example of an increasing sequence. Let b be a number which is greater than 1. Then we know that power function is an increasing function, hence this sequence b square, b cube, this is also an increasing sequence. And let us look at a decreasing sequence. If you look at this sequence 1, 1 by 2, 1 by 3, 1 by 4. So this is a decreasing sequence. And if you choose, if I take a to be a number which lies between 0 and 1, then we know that power decreases with the power of such number which lies between 0 and 1 decreases as the power increases. So this sequence is decreasing sequence. So there are huge number of decreasing as well as increasing sequences. So, but there are sequences also which are neither increasing nor decreasing, as can be seen this if I take -1 and 1. If you look at the first two terms, it seems that it's increasing, but if I take the next term, -3, then it is no more increasing. So if you have alternate terms with alternate signs, then this is neither increasing, this is neither increasing nor it is decreasing. So there are sequences which are not monotone. So you can say that this sequence is not monotone. So this is not a monotone sequence. So as other observations that can be seen from this definition of these increasing sequence, as can be seen this from this increasing sequence clearly, x1 is the lowest among all the terms of this increasing sequence. So when we can this x1 is a lower bound for this sequence. So increasing sequence is bounded from below. It is always bounded from below. And similarly, as can be seen that for decreasing sequence, the first term of the sequence is the largest among all the terms. So every term, every other term of the sequence, in case of decreasing sequence, is less than or equal to the rest every less than or equal to x1, and hence x1 becomes an upper bound, and therefore it establishes that this x1 is bounded from above. This decreasing sequence is bounded from above. It is bounded from above. So one side boundedness is always there in monotone sequences. In case of increasing, it is boundedness from below, and in case of decreasing, it is boundedness from above. So monotone convergence theorem says that if you have a monotone sequence which is bounded from both sides, then such a sequence is always a convergent sequence. So let me state this sequence and let me go to its proof then. Monotone convergence theorem. And for this theorem, let me use this abbreviation. And what it states that it says that a monotone, that means a sequence which is either increasing or decreasing, monotone sequence xn, which is bounded sequence, which is a bounded sequence, which is a bounded, a monotone sequence which is bounded is convergent. Or you can precisely say that a convergent, a bounded monotone sequence is always a convergent sequence. And further, uh, in case of increasing sequence, if sequence xn is increasing, then its limit as expected, since it is increasing, it is moving ahead, and its lower bound cannot be its limit, so its limit is expected to be its maximum or the supremum. Supremum of the terms or supremum of the range of this sequence will be its limit. And in case of decreasing sequence, if the sequence is decreasing, then its limit is going to be the range of its infimum. Limit of that sequence is equal to infimum of the range of this sequence. So from monotone convergence theorem, you can get that, you can find this supremum and infimum that will be their limits depending upon whether it is increasing or decreasing. For the proof, I will consider only increasing sequence, and parallelly the proof can be written for the sequence which is decreasing. So for the proof, let us consider a sequence which is increasing. suppose that sequence xn is increasing, and now since sequence xn is bounded, so it is bounded from above also, and hence supremum of this its range, since it's bounded from above, and a set which is bounded from above, its supremum always exists. That is what is the completeness axiom. So this number is always a real number. This exists, and this is a consequence of completeness axiom, or axiom of completeness, what you can say, completeness axiom of reals. So this is very important here. Indeed, this theorem is proved only by using this completeness axiom. Otherwise, we cannot prove it. This is required here. Or we can say that completeness axiom implies, or axiom of completeness implies monotone convergence theorem. So this supremum exists, and let this supremum be named as, let this supremum be denoted as x equals to, let me give it a notation. We are now sure that this is some real number, and let us try to prove that this real number, which is the supremum of this increasing sequence, is actually the limit of this sequence. Now we have to show that this sequence converges to x, and for this we have to show that the distance of the terms of the sequence for every epsilon greater than 0 becomes less than epsilon after n greater than equal to some natural number n naught. So let us take some positive number epsilon greater than 0, and first what I'm going to do, I'm going to apply the definition of a supremum, and the definition of supremum is that if I reduce this x by certain amount, or even a slightest amount, that then x minus epsilon will no more remain, will not be a supremum for this set. If it is not a supremum for this set, it's not a upper bound, and if it is not upper bound, there will be a some element which is greater than this x minus epsilon. So for this epsilon, by definition of supremum, I can say that there exists some natural number n naught great depending upon epsilon obviously greater than 0, such that x minus epsilon is less than x n naught. Now since your sequence is an increasing sequence, this is increasing sequence, so every other term is going to be greater than or equal to x n naught for every n greater than or equal to n naught. This is an increasing. So what it implies? It implies that x minus epsilon, which is going to be less than x n naught, and this is less than or equal to xn, and this is true for every n greater than or equal to n naught. But x is supremum of all these terms, so each of these such term is going to be smaller than or equal to its supremum, and I can write this x to be less than x plus epsilon. This last term I have no issue in writing it because it's always true. So if I drop this x from in between these inequalities, what is left to us is the following inequality, that x minus epsilon is less than xn, and this is less than x plus epsilon for every n bigger than or equal to n naught. And this inequality is nothing but this inequality is equivalently means that the xn mod of xn minus x is less than epsilon for every n greater than or equal to n naught. So what we have now, we have that for every epsilon positive, we have been able to extract an n naught, a natural number, such that after n naught, whatever n you take, then the term of the corresponding, then the distance of the corresponding term of the sequence from x is going to be less than epsilon, and that implies nothing but that the sequence xn is convergent, and it converges to the limit x, and it converges to x. Hence, this proves the theorem. This is so simple, no issue at all here. The proof is certainly a simple. The crux of the proof is that it utilizes the axiom of completeness. It depends on the axiom of completeness. Indeed, axiom of completeness completely implies that monotone convergence theorem holds. One can ask you this also, that prove that axiom of completeness implies monotone convergence theorem also. This may be also. We have also done a Bolzano-Weierstrass theorem. This also implies Bolzano-Weierstrass theorem, but that the proof we have omitted in unit 1, but in case of sequences it will be done in this unit. So okay, this was all about monotone convergence theorem, and I'm going to end up with an application of a monotone convergence theorem, a bit of non-trivial application, how we can sometime establish the convergence of the sequences which are inductively defined. Let us consider such a sequence. Let us consider a sequence inductively defined as follows. Let y1 be defined as to be 1, and all other terms are defined inductively. Yn plus 1 is defined as 1 by 4, 2 times yn plus 3 for every n bigger than or equal to 2. See then what happens? Then I'm going to establish that, then we claim that this sequence is convergent, and we will also find its limit also. And this equality, this recurrence relation will help us to find its limit, but this is valid. To find the limit of this sequence using this relation is valid only once you know with guarantee that this is a convergent sequence. For that, I'm just going to establish that it is a convergent sequence, and first and for that I will be taking the help of monotone convergence theorem. And for monotone convergence theorem, I need to establish that this sequence is actually a bounded sequence. If it is a bounded sequence, and then I'm going to finally establish that it's a monotone also. It is a increasing or decreasing, whatsoever it be, then we will be able to apply the monotone convergence theorem. Now first look at this thing, y1, 1, it is less than 2. Let us look at y2. Y2 will be 1 by 4, 2 times y1 is 1 plus 3, and it is 5 by 4, and obviously it is also less than 2. And next, let us suppose through induction, suppose that yk is less than 2 for some k, and I will apply the induction to establish that it's 2 is its upper bound. Then let us look at this yk plus 1. By definition, it is 1 by 4, 2yn plus 3, and since yk, since by induction hypothesis assumption this yk is smaller than 2, so this using this inequality I get this to be less than 1 by 4, 2 times 2 plus 3, which is equal to inside it will be 7 by 4, and clearly this is also less than 2, and hence by induction it follows that each term of this sequence is less than 2 for every n, and also clearly each term is a positive term, hence it is a bounded sequence. Since each term is a positive sequence, is greater than 0, hence 0 is its lower bound, 2 is upper bound. This implies that this sequence yn is bounded sequence. Next, we establish that this sequence is a monotone sequence. Look at the, again, I will use the induction method to establish it is an increasing sequence. Look at this, y1 is 1. And what is y2? Y2 is, by definition, it has to be 1 by 4. And it is 1 by 4 plus 2 times y1 plus 1. And it is what? It is, yeah, it is 2 times 3. Sorry, it is 3. It's not 1. It is 3. And so it will be 5 by 4. And clearly 5 by 4 is greater than 1. That what you can say y1. So in case we have y1 is less than y2. Next, let us assume the induction hypothesis that suppose that yk is less than yk plus 1, or less than or equal to, that's sufficient for some k, for some k. Then what happens, obviously it is strictly, we don't have equality, and then this implies that 2 times yk is also going to be strictly less than 2 times yk plus 1. It will not harm twice of this. If I add the same number to both sides, the inequality will remain intact. The order of the inequality will not change. I'm just adding 3 to both sides. And again, I'm multiplying by a positive number. Positive number multiplication by a positive number doesn't change the order of the inequality. I'm multiplying it by 1 by 4. This will be 1 by 4 2yk plus 1 plus 3. And look at this term. The first term in this inequality is yk plus 1, and the second term to the right of this inequality is yk plus 2. So this inequality carry on to the next term also. If it holds for k and k plus 1, it holds for k plus 1 and k plus 2 also. With this, it establishes that this sequence is increasing, is an increasing sequence, is an increasing sequence. So now this is increasing, this is bounded also, hence by monotone convergence theorem, it is convergent. As we saw in the convergence, in the definition of, in the statement of the monotone convergence theorem, that told you about that the limit of this increasing sequence is going to be supremum. But in case of this inequality, here we have the terms are given inductively, and finding supremum is not an easy job here. And we will use a technique which works for such sequences plus 3. And finding supremum for this term is not an easy thing here. But what helps us here that since yn is a convergent sequence, is convergent, and yn plus 1 is its tail, is its one tail, I will call it. One tail means only first term is not included in this sequence. It is a one tail, and so it also converges to the same limit to which yn converges. And also it converges to the same limit, to the same limit to which yn converges. This is true in case of sequence, convergent sequences. That if a sequence is convergent, then each tail of this sequence converges along with it to the same limit. And let us take y to be a limit of this sequence yn. Then that means that y is the limit of its tail yn plus 1. Now if you use the if you use the concept, if you use the results where a convergence and algebraic operations interact, then I will have from this in equation, I will have that limit of y n plus 1 will be equal to 1 by 4. I can take, because sum of convergent sequences is a convergent, and multiplying it with scalar hardly affects the convergence. It is yn plus 3, and this gives us a equation which is being satisfied by y. It is 1 by 4 2y plus 3, and what it gives us, it gives us that y is equal to 4 times y equals to 2y plus 3, and this gives us, if I take 2y to the left hand side, I will have 2y equals to 3, and from here I get the value which is the required value of the limit of the sequence yn. So this is a trick here, but this trick works only when you know that such a sequence which is defined inductively is convergent. You have to establish it's convergent, only then this is the valid thing. Otherwise, if the sequence is divergent, you may also still get a value of y, but which may not be a valid thing to uh, depend on. Students, I'm going to give you another application of this monotone convergence sequence, which helps us to find a square root of a sequence, and we will also establish a number which is an irrational